All right, so here we have our thermochemistry review. So we're going to go through each one of these questions. This first one lists four characteristics of an exothermic process and lists two examples. I'm not going to write this down. I'm just going to talk about it. So, four characteristics of an exothermic process. Number one, energy is being released. Number two, it feels hot because that energy that is being released is absorbed into your hand or body or whatever that is touching it, and your body perceives that as feeling hot. The energy of the products is always going to be lower than the reactants, okay? Because the reactants have energy, they release that energy as they turn into products, and so therefore the products will have less energy than the reactants because that energy was released. And last, heat flows from the system to the surroundings. Okay, so if you were to touch a exothermic process, then that heat is flowing from the system, the exothermic process, into your hand, which is the surroundings, which again is why you feel heat. A couple examples: there are hot packs. So, like if you one of those things where you break, and the chemicals mix together and that produces heat. That is an exothermic reaction. Also, burning logs. So if you are just basically burning anything, that is an exothermic process. So next one, list four characteristics of an endothermic process and two examples. So basically, it's all the exact opposite of what I just said. Okay. So for an endothermic process, energy is absorbed instead of released. It feels cold because energy is being absorbed into that process. So, like if you were to touch it, it is absorbed, taking energy away from your hand into the process, which is why it feels cold. Which brings us to the next part. It feels cold. Um, the energy of the reactants is lower than the products. So, energy of reactants, there isn't very much energy. It needs to absorb energy in order to react. So, once it absorbs that energy, the products then have that energy, and the products then have more energy than the reactants. And then heat flows from surroundings to the system. Okay. A couple examples are ice melting and water boiling. All right. So, we kind of already talked about this up here, but in an endothermic reaction, heat flows from the surroundings to the system, and in an exothermic reaction, heat flows from the system to the surroundings. All right, so now we are going to do some conversions. So, first one, we have 14 big calories to joules. So we write down our given 14 big calories over 1. We're going to joules. So our first conversion factor, we need big calories at bottom. We cannot go right from big calories to joules. We have to go to little calories first. So little calories goes on top. There are 1,000 little calories per one big calorie. Big calories cancel out. We're left with little calories. That is not where we want to be. So we need another conversion factor. Little calories on bottom, joules on top. There's 1 little calorie per 4.184 big calorie. I'm sorry, joules. Little calories cancel out. We're left with joules. That is where we want to be. We do our math and we get 59,000 joules. All right, so next we have 190 little calories to joules. So we do our first conversion factor, little calories. We can go right from little calories to joules. 1 little calorie per 4.184 joules. Low calories cancel out. We're left with joules. That is where we want to be. So we just do our math, and that turns out to be 790 joules. Last one, joules to calories. So we write our given 3848 joules over 1. We do our conversion factor, joules on bottom, little calories on top. There's 1 little calorie per 4.184 joules. Joules cancel out. We're left with calories, little calories. That is not where we want to be. We want to be at big calories. So we put little calories on bottom. We put big calories on top. There are 1,000 little calories per 1 big calorie. Sorry, little calories cancel out. We're left with big calories. That is where we want to be. So now we do our math. We get 0.9197 big calories. Okay, units in order from largest to smallest. I'm sorry, smallest to largest. So the smallest unit is the joule because there are 4.184 joules per 1 calorie. Okay, then we have little calories. Then we have kilojoules. And then we have kilocalories, also known as big calories. That is the order from smallest to largest. All right. Next, we have some labeling to do. Okay, so we'll do that so we can see all of it. There we go. All right, so this first one here, this is an endothermic reaction. So endo. And the reason we know that is because we have our reactants here and our products here. The products have more energy than the reactants. So that is an endothermic reaction. Okay, so that means this one is exothermic because products have less energy than the reactants. Okay, next, energy of the reactants. Okay, so that's going to be at the very beginning. So that's this right here. Okay, wherever it starts, that's the energy of the reactants. Energy of the products, that is this right here. Okay, sorry, that's why I wrote a C there. That's energy of the products, wherever it ends. Activation energy. Activation energy is the energy that is required to get the reaction started. Okay, so that is this hump right here. So the difference between the reactants and the top of the hump is the activation energy. So that's D. So for this one, it's that amount. Okay. Oh, and I guess we can do the math there. So this one, it looks like at reactants are at about 325. The top of the hump is at 500. So we just subtract those and we get 175 for this one. Okay, so for this one, it's a little easier. 350 is where the reactants are, 450 is where the top of the hump. So the activation energy for that one is 100. Okay, so that was D. Next is the activated complex. So the activated complex is just the spot right at the top of the hump. Okay, that is when the reactants kind of start melding together and start producing the products, but they haven't quite gotten there yet. It's like the interim between reactants and products. It's right at the top of the activation energy. And last is the delta H. Now the delta H, so F, is the difference between the reactants and the products. So reactants for this one is right here. The difference between the reactants and the products is our delta H. So for this one, it's right here, all the way to the reactants. There we go. That's our delta H. Okay. Next, calculate the delta H of each reaction. What does delta H? Oh, we already did that. Oh, no, we didn't. We did the activation energy. Never mind. Okay, so delta H. We find the products, which is 400. We find the reactants, which is 325. So our delta H for the first reaction is 75. Okay, and that's positive 75 because it's products minus reactants. So it's going to be 400 minus 325, which is positive. Okay. Now this one over here, it's going to be 250 minus, I'm sorry, 275, my fault. 275 minus 350, which turns out to be negative 75. Because we have to do products minus reactants. Okay. Okay. So next is number 8, and that's going to be using this equation here. So this is our thermostoichiometry. We are given one given, that usually means it's going to be thermostoichiometry. Okay. So when with thermostoic, we write down our given grams of hydrazine, which this is hydrazine, so that's N2H4. Okay, we put that over 1. We do our first conversion factor. We have grams of N2H4, that, and then we're going to convert that to moles. Okay, 1 goes in front of moles. The molar mass of N2H4 goes in front of grams, so that's going to be 32.06. That cancels out. We are left with moles. Whoop, I forgot to write that again. N2H4, which is not where we want to be, so we need to do another conversion factor. And actually, we're going to rewind a second. Calculate the change in enthalpy. So we are looking for energy. Okay, so that's why we didn't stop here at moles. So moles goes on the bottom here. Moles N2H4 goes on the bottom. We are looking for energy, so kilojoules goes on top. This is the mole to energy ratio. So we're going to use our coefficients. Now, since the coefficient of N2H4 is 1, we're just going to put a 1 there. And kilojoules is our delta H, so that's negative 420.0 kilojoules. Moles of N2H4 cancel out. We're left with kilojoules. That is where we want to be. So we are just going to do our math. So we get negative 333 kilojoules. All right, next one. We are given 1.45 moles of HCl. So we do that for our given 1.45 moles HCl over 1. We do our conversion factor. Moles goes on bottom. Okay, now since we are starting with moles, we don't have to worry about converting to moles, so we don't need our molar mass. So all we need is our mole to energy ratio. So kilojoules goes on top. Since this is our mole to energy ratio, we need our coefficient for HCl, which is 4. And then we need our enthalpy, which is negative 420.0. Moles cancel out. We're left with kilojoules. That is where we want to be. So we just do our math. That gives us negative 152 kilojoules. Hooray. Okay, so, oh, sorry, I'm doing this at school and there's the bell. Okay, cool. All right, so next, calculate the change in heat when 45.32 grams of magnesium oxide is produced. So we do our given 45.32 grams of MgO for 1. We do grams of MgO, moles on top. 1 next to moles, our molar mass next to grams. Grams cancel out. We're left with moles. That is not where we want to be, so we need another conversion factor. Moles MgO on bottom. We are going to energy because it's calculate the change in heat, so that's energy. So kilojoules on top. This is our mole to energy ratio, so coefficient, which is 2 right there. And then our enthalpy, which is negative 288. Oh, that's kilocalories, actually. So, kilocal. There we go. 288 kilocal. Sorry about that. All right. So, moles of MgO cancel out. We're left with kilocalories, which is where we want to be. So now we do our math. We get negative 161.9 kcal. Next one, calculate how many grams will be produced if that many kcals are produced. So 1,356 kcals are produced. Now, since that's the amount of energy that is produced, that means it's going to be negative. Okay, so when we do our conversion factor, kcal on bottom, moles on top, moles of MgO. This is our energy to mole ratio, so we need our coefficient next to MgO. We need our enthalpy, which is negative 288. kcal cancels out. We're left with moles of MgO. That is not where we want to be. We want to be at grams. So we need another conversion factor. Moles MgO on bottom. Grams MgO on top. One next to moles. Molar mass next to grams. Moles cancel out. We're left with grams. That is where we want to be. So that gives us 379.6 grams of MgO. Okay. Now, just to kind of clarify, this negative here, that was very important because our enthalpy is negative. And so this negative and this negative cancel each other out. Okay. If we didn't put this negative here, there we go. If we didn't put this negative here, then our end answer would have been negative. And you cannot have a negative amount of grams. It just doesn't work. Okay. So if energy is produced and it's your given, it needs to be a negative. Okay. All right, so next, the specific heat tells us about a substance. The specific heat tells us the amount of energy required to change 1 gram of that substance by 1 degree Celsius. So in a little bit more simplistic terms, it tells us how easily, quickly, and efficiently energy can transfer through that substance. The size of the specific heat, so if it's a really big specific heat or a really small specific heat, if it's a large specific heat, that means it is difficult to change the temperature of the substance. So a lot of energy is required to change the temperature of the substance. So for example, water. Water has a very high specific heat of 4.184. So it takes a lot of energy to change the temperature of water. Whereas metals have low specific heats, which means it does not take very much energy to change the temperature of a metal. Okay. All right, so what is the specific heat of aluminum if the temperature of a 56.8 gram sample of aluminum is increased by 9.2 degrees Celsius when 454 joules of heat is added? Okay, so our equation is Q equals MC delta T. Okay, so from here, we need to identify what our givens are. So we have 56.8 grams, 9.2 degrees Celsius, and 454 joules. Okay. So our first one, 56.8 grams, that is our mass because it says grams. So 56, oh, that's a 9. Numbers are hard. 56.8 grams. Next one at 9.2 degrees Celsius. It's increased by that much, so that means it is the change in temperature, which is delta T. And 454 joules, that's Q because joules is energy. Okay, so from here, we need to rearrange our equation. We are looking for C. So we have to get C by itself. To get C by itself, we have to divide both sides by M delta T. That way M cancels out and delta T cancels out, and we're just left with C. So I'm going to erase all that other stuff. There we go. So now we have Q over M delta T equals C. So now I just plug in our numbers. So it's going to be 454 joules divided by 56.8 grams times 9.2 degrees Celsius. And we get 0.87. Now, since none of these units cancel out, we are going to use all of them. So our unit for C is joules per grams degrees Celsius. There we go. All right, next one, same situation. We have to identify all our givens and then plug them into our equation. So we have 15.34 grams. That's mass. 34 grams. Next, we have two different temperatures. Okay, so it says when the temperature goes from 76 to 102.9, that means that is our initial and final temperature. So since we have an initial and final, all we have to do is find our change in temperature. So we do final minus initial. So 102.9 minus 76 is going to be 26.9. Degrees Celsius. Okay, so that's our delta T. And then our C is 0.129 joules per grams degrees Celsius. Okay, so now our equation. Q equals MC delta T. Okay, our what we are looking for is how much heat is absorbed, so that's Q. So we don't have to rearrange anything. We just plug it in. So 15.34 grams times 0.129 joules per grams degrees Celsius times 26.9 degrees Celsius. And that gives us 53 joules. Okay, because grams is right here, grams is right here. It's on bottom here, so that cancels out. Degrees Celsius right here, degrees Celsius on bottom right here, so that cancels out. We're left with joules. And there we go. Okay. Next, we have 29.87. So that is our mass. Mass equals 29.87 grams. Absorbs 79.89 joules of heat. So that's our Q because that's energy. Well, starts out at 64.6. What is the final temperature of the metal? Okay, so we're looking for final temperature, which means we need to find change in temperature from our equation. Okay, our specific heat is 0.52 joules per grams degrees Celsius. So C equals 0.52 joules per grams degrees Celsius. Okay, our initial temperature, so TI equals 64.6 degrees Celsius. Okay, so our equation, Q equals MC delta T. We need to find delta T. So to do that, we have to divide both sides by MC. So MC there, M and C cancel out. So we're just going to erase those. So Q over MC equals delta T. Okay, so our Q, 79.87 joules, divided by our M, 29.87. 7 grams times our C, which is 0.52 joules per gram degree Celsius. And for that, we get 5.1 degrees Celsius. Okay, now that is our delta T, but it is asking for our final T. So what we are then going to do is add those two together. So we're going to take 64.6, that's our initial T, add it to 5.1, and we are going to get 69.7 degrees Celsius. There's that. Okay, so how does the energy change of a system compare to the energy change of the surroundings? So this is calorimetry. However much the energy changes in the system, the surroundings changes by the same amount of energy, but it's the opposite. So the negative of it. So if a system releases 5 joules of energy, the surroundings absorbs 5 joules of energy. Okay. So a 20.26 gram sample, I'm not going to read the whole thing, I'm just going to do numbers. So 20.26 gram sample, unknown solid. So that is going to be our mass. Okay. That is going to be our mass of our metal. So we're going to call that M1. So that's 20.26 grams. It's heated to 78.3 degrees Celsius. Okay, so that is going to be our initial temperature. So Ti of 1. So that's 78.3 degrees Celsius. Placed into a calorimeter containing 43.83 grams of water. So that's our M2. That equals 48. I'm sorry, 43.8. 43.83 grams at 30 degrees Celsius. So that is our initial temperature of 2. So that's 30.7 degrees Celsius. So our final temperature is 33.3 degrees Celsius. So TF equals 33.3. So I put that in the middle because that is the final temperature of both substances because you're mixing them together. So that means whatever the final temperature of one of them is, it's going to be the same as the other one. So to get the change in temperature, we just subtract those two. So it's always going to be final minus initial. So 33.3 minus 78.3 for that one. 33.3 minus 30.7 for that one. So this one's going to give us a delta T of 2.6. So that's delta T of 2 because that's the water. This one is going to give us a delta T of negative 45.0 degrees Celsius. Oh, I forgot to put degrees Celsius over here. There we go. And that is delta T of 1. There we go. All right. So that takes care of all our temperatures. If the final temperature of a solid sample and water is, oh, we already said that. What is the specific heat of the solid? Now, the other thing is, it doesn't give us the specific heat of the water, but we know that the specific heat of water is 4.184 joules per grams degrees Celsius. All right, so now our equation, mc delta T equals negative mc delta T, because the energy of the system is equal to the energy of the surroundings, but a negative of it. Okay? So now we are looking for the C of our system. So that's C1. Okay, so we're looking for this right here. All right. So we have to divide both sides by m delta T in order to get that C by itself. T, there we go. So m and delta T cancel out. I'm just going to erase those. All right, so there we go. Now we plug everything in. So we have, and this is, so we have 43.83 grams times 4.184 joules per gram degree Celsius times 2.6 degrees Celsius divided by our stuff over here. So negative 45 degrees Celsius times 20.26. Okay, and there is that negative up here. So we do all that math. This negative cancels out this negative, and we eventually get 0.523 joules per grams degrees Celsius. And that turns out to be titanium. Hooray. Okay, so last question. Unknown mass of water, blah, blah, blah. So very similar to last question, we are going to identify each one of our numbers as a variable. Okay, so our first one, hold on, there we go. Our first one, 58.3 degrees Celsius. That is our initial temperature. So Ti, and that is of water. So that's Ti2 equals 58.3 degrees Celsius. Okay, it is mixed with 25.5 grams of ethanol. So 25.5 grams of ethanol is mass 1. So that's 25.5 grams at 44.0 degrees Celsius. So that is Ti of 1. That's 44.0 degrees Celsius. The final temperature of the mixture is 52.8. Okay, so that is our final temperature of both. So 52.8 degrees Celsius. All right, now to get the delta T, or change in temperature for each, you take 52.8 minus their initial temperatures. So for the water, that's going to turn out to be delta T equals negative 5.5 degrees Celsius, because it's final minus initial. And for the for the ethanol, the delta T is going to be 52.8 minus 44, which is 8.8 degrees Celsius. And that one is going to be positive, since it's 52.8 minus 44.0. Okay, so next, the specific heat of water and ethanol is that what is the mass of water? So for water, I forget which one's water now. First one, okay. Oh, and that should be delta T2. That should be delta T1. Okay, so delta T, specific heat of water is 4.184 joules per grams degrees Celsius. That's 2. Specific heat of ethanol is 2.44 joules per grams degrees Celsius. Okay, so now we have to find the mass of water. Our equation is mc delta T equals negative mc delta T. Okay, so we are looking for, sorry, I should do this. This is 2, this is 1. So we are looking for the mass of water. So mass 2, 2, there we go, equals question mark. So we want to get mass of water by itself. Okay, so we got to divide both sides by C delta T. And then we need to, on both sides, sorry. So C delta T is going to cancel out on this side. So we are now just going to plug in our numbers. So that's going to be, I'm going to scroll down here a little bit. So that's going to be 25.5 grams times 2.44 joules per grams degrees Celsius times 8.8 degrees Celsius. So that's all the ethanol stuff. So that's all this side stuff. Okay, that goes on top. Then the water stuff is going to go on bottom. So 4.184 joules per grams degrees Celsius times negative 5.5 degrees Celsius. And there's also a negative up here because that is in the equation. So this negative and this negative will cancel each other out. And then we do our math and we get an overall answer of 23.8 grams of water. And that is that.